Welcome back. The year I'm making this video is 2015. Just thought I'd mention that since it's February now while I'm making this video. And February is an important month. We celebrate Lincoln's birthday, Washington's birthday, and the oh-so-important Valentine's Day. But something you may not know, that down in Argentina they celebrate in February the National Day of the Sun. So there you go. Learn something new every day. Well, hopefully these videos will help you learn how to find the maximum error when using a polynomial function to approximate the value of a non-polynomial function. So we're going to go ahead and get right into example 7. We're trying to figure out how closely the fourth degree Taylor polynomial for cosine of x, and so let's go ahead and write that out, approximates the true value on the interval from negative 0.5 to 0.5. So well, we know that the cosine of x Taylor polynomial, first of all, we want to make sure we're on the right interval. You should notice here, if we're trying to figure out how to approximate the value on this interval from negative 0.5 to 0.5, that the center, that we're centering our polynomial at 0. So we do have a Maclaurin polynomial, and so we know that the cosine of 0 is 1, and so our first term is going to be a 1, minus x squared over 2 factorial plus x to the fourth over 4 factorial. And that we also, we know we need to add a remainder, fourth degree remainder of x, and so that's what we're going to focus on right now. How big is that remainder possibly going to get? Okay, well, we know that the remainder of degree 4 is equal to the fifth derivative, so the fifth derivative at some point z, multiplied by x. I was going to write x minus something, but the something is minus 0, so I'll just leave it as x to the fifth power over 5 factorial. Well, what we're really doing here is we're going to be, we're noticing negative 0.5 to 0.5. Well, on any interval from right around where the polynomial is centered, we know that we can either go left 0.5 or right 0.5, but let's just go ahead and go to the right 0.5 and let's estimate the maximum value that R4 of 0.5 can be, and then I'll talk about how we handle the negative 0.5 as well. But let's go as far away from center as we can to the right, and we're going to take R4 of 0.5, and then that's going to be, if we take the absolute value, we're always talking about positive numbers here, that remainder is going to be less than the absolute value of this guy here. Let's just put in the 0.5 to the 5 right there over 5 factorial, and all we have to do is figure out right here the maximum value that the fifth derivative of cosine can possibly be. Well, we talked about that in class. We talked about successive derivatives of sine in class, but if we talk about successive derivatives of cosine in class, we should know that they toggle in between cosine and sine with some minuses and positives in there. And so we know, though, that either the cosine or sine or even negative can get no bigger than 1. Okay, so if we know that the maximum value that this guy, the fifth derivative, can get would be 1, then we're going to replace in our expression a 1 in place of that fifth derivative, because we have an upper bound for the fifth derivative. So we call it the Lagrange upper bound, but nevertheless, knowing how to get it is more important than knowing what it's called. So we have this guy here, and we know that we don't have any variables in there, so we can just type that into the calculator. And if you do type that into the calculator, you're going to get 0.0002604. You might get an error a message on the calculator that says something like 2.604 e minus 4, something like that. Well, that's translated as 2.604 times 10 to the negative 4, and times 10 to the negative 4 means that we're going to take the decimal and go 1, 2, 3, 4 to the left, and then those empty buckets we fill them with zeros, and we get our maximum error. Okay, so that's how we get our maximum error. And let's go ahead and complete this sentence, though. This is important that you're able to articulate what this means. we're going to replace, we're going to put right here 0.0002604. Okay, let me zoom in a little bit here. So we have 0.0002604 represents the maximum error when using that polynomial to approximate the cosine of x on the interval from negative 0.5 to 0.5. Now let's address the issue of why didn't we go to the left 0.5 and why did we go just to the right 0.5? Well, if we replaced 0.5 here with negative 0.5, we know that the fifth derivative of the cosine can still get no bigger than 1, so we'll still replace that number right there with a 1. Then we would replace this number right here. Instead of writing 0.5 to the 5, we'd write negative 0.5 to the 5, and then we would get the same exact value as what we have here, except that we'd get a negative number, but the negative number inside the absolute value bars is going to make it positive. The absolute value bars will make it positive, so we still get the same maximum error whether we go to the left to negative 0.5 or to the right at 0.5. And it should be noted also that we didn't choose a value in between 0 and 0.5 because we know the further we get away from 0 on the number line, either left or right, the further away we get from 0, the greater the error is going to be. Okay, so we could have chosen 0.4 here, but that would have given us a smaller error than what we got here. But again, we wanted the maximum error, how closely the fourth degree polynomial for cosine approximates the true value of on the interval. Okay, well, if we go as far away as we can from 0, then we get our maximum error. And then again, make sure that you can articulate what I wrote down here, is that number and then what we talked about represents the max error when using this polynomial to approximate cosine of x on the interval from negative 0.5 to 0.5. I think you'll find example 8 a little bit different, so I'm going to make that in a separate video, and I'll see you then.